Okay, one last video for this module. Now we'll just kind of briefly summarize research methods in the social sciences. Um, and so, once again, we're a science, right? We're using the scientific method, something you've probably learned about throughout your academic career and education. So to kind of just briefly summarize it again. So basic sense, we're stating a problem or a question, right? Something we're unsure of or want to understand more about. And then in order to understand it more, we need to design some way to study it, right? Some way to meticulously think through and seek an answer to our question. So we'll design a study, we'll gather our data, we'll analyze the data, and then we'll draw conclusions. And this is a continuous process, typically in any study. After we've drawn our conclusions and finished the study, we'll have new questions or new things we're unsure of. Right, so say I want to study something. Let's see, what do I want to study? Maybe I want to study people's preferences in some trail system, right? So which trails people prefer. And some I don't know, maybe like Birch Hill outside of Fairbanks or something. Right, we're looking at cross-country skiers. We want to see what people prefer, or if people ever make wrong turns, maybe. We could design some study to do that. We could set up some trail cameras, ask people's consent. We could put people out there to just watch people, right? Whatever it may be, gather our data, analyze our data, draw conclusions, and determine what people do if they're making wrong turns. I don't know, maybe that's a terrible example, but this is a quick one off the top of my head. But in whatever sort of question we're trying to answer, here are some of the common methods we might use. Again, not exclusive or comprehensive, but some of the most common ones in social science research. Let's start with experimental. So in an experimental design, the key strength is that we can assess cause and effect. And we need a high level of control in order to do that. Like, for example, if I wanted to do a study on whether, let's see here, whether melatonin, whether melatonin helps people sleep, right? In order to truly isolate if melatonin is causing that, I basically have to monitor everything about people's lives, right? Because their diet is going to play a role, their exercise, their other health conditions, their typical sleep habits, their sleep environment, the quality of their mattress, right? There's just so many other things at play. So I've known people who do sleep research, and they basically have to bring everyone into a lab and observe them around the clock for a long period of time. And so this is very useful in that we can isolate cause and effect, but it's also typically very resource intensive in order to do that. It's just hard to do. But in a basic sense, we're manipulating things to see how they affect other things, right? We're manipulating independent variables to see how they affect dependent variables, right? And one way to kind of keep those separate in your head is that dependent variables depend on the independent variable, right? So here, sorry, I'm messing with my pointer so it stops disappearing. So say, for example, I want to see how melatonin affects sleep. I want to see if sleep depends on melatonin, the independent variable, or if quality of sleep depends on melatonin. So some requirements to be an experiment: manipulation, right? So we're varying the independent variable. I might give people 10 milligrams of melatonin, 5 milligrams of melatonin, and no melatonin, right? So I might put them in different groups that way. Randomization, right? So there are different groups, but there's an equal chance of being selected for any of those groups, right? So ideally, our entire population has the same chance of being randomly selected for the study and for the different groups, and some sort of comparison or control group, right? And so in this example, if we had a group where they got no melatonin, right? So in other words, the level of the independent variable, the level of melatonin is 0, right? Or 0 milligrams. They might just get a sugar pill for placebo. So to put it in another example, let's say we wanted to do a study on if cardiovascular exercise influences depression. Right, so yeah, so basically cardiovascular exercise, any sort of thing that's, I actually don't know how you describe cardiovascular, but basically stuff that gets your heart rate up, right? So let's see, like running, for example, or swimming, something like that. So in a basic sense, our dependent variable is depression, and our independent variable is exercise. I spent way too long on that animation back in the day, so I have to keep using it. But say I wanted to group people into different experimental groups for this study, right? Or actually, I kind of use that term incorrectly because the experimental groups are the ones who are receiving treatment, right? So say one group is running 1 hour a day, one group is running 30 minutes each day, all right? And then the control group, which gets 0, is getting no exercise, right? That's an example of how we might categorize this. Kind of brief, but something you'll probably learn about in a variety of classes if you haven't already. Quasi-experimental, quasi-experimental methods. Basically, it's an experiment, except it's not quite as rigorous, right? So typically something isn't up to the standards of an experiment. So it's a close second to an experiment, but it's not quite as good at isolating cause and effect. So it might have a non-manipulated IV or classification variable, might have a lack of random assignment to groups, or a lack of a control group. So some examples to articulate what I mean by that. Say I wanted to look at if there's a difference in aggressive behaviors across genders or gender identities, right? I can't manipulate people's gender, right? That'd be really messed up. And yeah, I'm not even going to go any further with that scenario, right? It's not something we can manipulate, right? So that's an example of a time when we can't really do an experiment because we can't manipulate the independent variable or people's gender. We can ask people their gender identity and then look at them, look at the effect or the difference between aggressive behaviors within or between genders, but we can't actually change gender. Example 2, or we can't change it without their consent. Yeah, we'll stop there. Moving forward. So example 2, do different work groups differ in number of supported behaviors? Kind of another example where we really can't manipulate the IV and we can't randomly assign people to groups, right? Because say I'm some consultant and I'm doing a study with an organization and they already have these pre-existing work groups, I can't just switch up their entire organization, right? People are in the work groups that they are, so we can't randomly assign them, but we still want to see if there are some differences there. Or another example, are there differences between 20 and 40-year-olds in reaction time? There's no such thing as a control group for this study because there's no such thing as someone with no age, because that's a person who just doesn't exist, right? They're either dead or they've never existed, they've never been born. So we just can't have a control group there, right? So some examples of when we want to study something using as much experimental research standards as we can, but we can't quite reach the level of rigor that we need for an experiment just because of the nature of the parameters or boundaries of our study. And last one, correlational. You've probably heard of correlations before. This is a word that seems to have entered the lexicon in general. Like people use the word correlate in ways that I hadn't heard when I was younger. When we talk about it in statistics, though, correlational analyses, we're trying to quantify the strength and direction of a relationship between two or more variables. So for example, if we're using 2, we'll say x and y. And so basically this is, we can like chart our x and y's for all these different individuals, and then look at the relationship or the pattern across the entire sample, right? So each of these dots represents a case or a subject. I don't know, what's an example here? I'm not going to spend time trying to think of an example, but here you can see for this person, their X score was about 2.8, almost 3. Their Y score was 2, right? And so each of these points represents a person. Then we can plot an overall relationship between the X and the Y variable. If graphs aren't really your bread and butter, you might think of it in terms of Venn diagrams, right? So how much these two things kind of overlap with each other. And so when we do correlational studies, we'll talk about correlations at the end of the semester, but I wanted to mention these briefly for now. So whenever we do a correlational analysis, we'll get some correlation coefficient, right? Something that indicates the strength of the relationship or how closely things vary together. And these numbers can range from -1 to +1, and the direction is indicated by the sign. So we'll talk about this in more depth. So if a correlation coefficient is positive, that means that the two things increase or decrease together, right? If one goes up, the other goes up. If one goes down, the other goes down. If it's negative, it means that relationship is inverse, right? So as one goes up, the other decreases, and vice versa. And so I kind of think of this like if you need an example to help put that in context. Sometimes I describe this as like you can think of if they're positive, it's kind of describing like a friendship almost. If you have a positive relationship with someone, you probably want to hang out, right? If they're going to the movies, you want to go with them. If they're going, I don't know, to the library, you want to go with them, right? So you kind of go places together. A negative relationship with someone, you probably want to stay away, right? So if they're going and sitting at that table, I'm going to go to the other side of the room, right? So kind of just one way to kind of think of this and give some context to it. So some examples to kind of test your knowledge. What do you think? Is this a positive or a negative relationship between hours spent studying and test scores? Say I give you a test at the end of this week. What do you think? You can pause the video if you need some more time. The answer, hopefully you're ready for it, is a positive relationship, right? The more hours you spend studying, generally speaking, the better your test score is going to be. It's not a perfect relationship, but it's still generally we can assume that this is going to be positive. Or say we did say we were looking at like that cardiovascular example, miles ran per week and weight, right? What do you think here? Hopefully you're ready for it. This would be negative, right? For most people, the more you're running, the less you're going to weigh, right? Because you're just burning more and more calories. Okay, and so that's a little bit about the sign, right? The direction of the relationship. The strength of the relationship is indicated by the absolute value of R, right? Or just what the number is. So closer to plus or minus 1 is stronger. So to put that in context, so if we have a correlation of 0, it means the two things are not related, right? They're essentially separate, or there's no overlap here between the two. As we go up in a positive direction, right, we can see that there's more overlap. So correlation of 0.5, there's much more overlap. A correlation of 1, now essentially it's a perfect relationship, right? As one goes up, the other goes up in the exact same quantity, right, or consistency. So you can see examples of what this would look like on scatter plots. The strength of those relationships, 0.5, 0.9, and 1. And so at 1, it's essentially a straight line, right? Because again, as one goes up, the other goes up in the exact same quantity. And then if we're looking at negative correlations, and I should have mentioned, here's a scatter plot for no correlation. Right, you can see there's essentially no line we could draw through this. And then as we go down into negative correlation, right, there's still overlap in the same quantity. It's about the directionality of the relationship, right? That's the only difference between minus 0.5 and 0.5. And then minus 1, it's, again, a perfectly negative relationship, right? So now it's still a straight line, but it's pointing down, right? So as one goes up, the other goes down in the exact same quantity, right? And so putting this all in context here, you can see that, again, the number itself, the absolute value, represents the strength, right, or how tightly packed together these data points are in the scatter plots. And then the sign, positive or negative, just indicates the direction of the relationship, right? Is it positive? Do they increase and decrease together? Or is it negative? Do they increase and decrease inversely? And so the strengths of correlations is that we can study things we can't manipulate, right? We don't even have to. We just need some way to measure it, and we can look at correlations, right? Some way to basically quantify it. And we can see how things fluctuate, right? Do they fluctuate together? What tends to go together? What tends to not go together? But the key weakness here and the key thing to remember is that correlation does not equal causation, right? Something I hope you've heard by now, but if you haven't, I really want to drill into your heads. Correlation does not equal causation. In fact, I don't care what you're doing, say it with me now. Correlation does not equal causation, right? Experiments tell us if one thing causes another. Correlations do not. So a hypothetical example to articulate that point. So say I'm doing a study and I find that motivation is positively correlated with performance at 0.5. What are the underlying mechanisms that explain this relationship, right? So say we're doing this in, let's give a little bit more context. Say I'm doing this with students, right? And so I find that students' level of motivation to succeed, right, to study, to be a good student, is positively correlated with their overall performance in the course, right? Makes sense, right? They're more motivated, they tend to do a bit better. Yeah, so if you want to figure to help see that, right? So we're seeing that these increase together. More motivation means more performance, and vice versa. Well, I wonder what's causing this, right? Or if we're trying to infer causality, maybe we would assume, okay, it's motivation that's causing performance, right? They do well because they are motivated to do well. Okay, it's possible. However, the opposite could also be true. Maybe it's that the better you do at something, the more motivated you are to continue doing well, right? Because you're getting that positive feedback, right? It's like if you go and work out at the gym and the more you're working out, the better you feel. And so you're just motivated. You're like, I'm crushing it. Let's keep it going, right? So maybe it's the opposite, right? Maybe it's that performance is causing motivation. Maybe it's something else, though, right? Maybe it's effective leadership, right? In this case, it's because your instructor, me, is so damn charismatic and good at his job that you're just motivated to do well and you're performing amazingly, right? I'm just kidding. I don't have that big of an ego. And I wouldn't presume to be the cause of all of this. But just one hypothetical, right? Maybe it's something about the leader or the person who is mentoring that individual, that student. Or maybe I need to get over myself because it has nothing to do with me and it's all about you, the student, right? Maybe it's your individual characteristics. Maybe some people are just more motivated and perform better, right? Maybe it's something about their personality, their past experiences, right? Something about them that explains all that. Yeah, or maybe it has nothing to do with that, like their personality, right, or stuff like that. Maybe it's just if they're sleeping well, right? Maybe one of them has their own room in a quiet basement, and the other person is in a dorm where there's just someone partying right next to them every single night, right? And so maybe sleep quality is affecting their motivation and their performance, right? And so hopefully you see my point here. It could be a million other things explaining this relationship. And so one correlation alone never tells us what causes what, right? We're only seeing that they're related in some capacity. Right, so once again, correlation does not equal causation. This comic is really blurry. So if you can't read it, it says, I wish they didn't turn on that seatbelt sign so much. Every time they do, it gets bumpy. Right? This is an example of someone inferring causation from correlation when it's not the case. Right? Thinking that the seatbelt sign in airplanes causes the bumps, right? When really the bumps are what causes the pilot to turn on the seatbelt sign. And so something I wanted to wrap this up with is something called spurious correlations, basically meaning that if we look at enough variables out there and assess enough things, sometimes we'll find correlations or things or relationships numerically that don't have any practical sense or any grounding in reality. So an example to explain what I mean. There's a whole website called Spurious Correlations that you can look these up on. So an example here, the number of people who drowned by falling into a pool correlates with films Nicolas Cage appeared in. All right, and you can see the line here. This is a pretty good relationship, right? So you might say, okay, well, we need people to, or we need Nicolas Cage to stop doing films because he's killing people, right? All these people are drowning as a result. Or maybe you love Nicolas Cage and you're like, you know what, more people are going to have to take the hit and drown that way that he can get more film contracts, right? Something like that. Another example, the divorce rate in Maine correlates with per capita consumption of margarine, right? So people need to stop eating all that butter because it's wrecking their marriages, right? Letters in the winning word of the Scripps National Spelling Bee correlates with the number of people killed by venomous spiders. So in other words, how long the word is in terms of letters that people had to spell to win the spelling bee correlates with how many people get killed by venomous spiders, right? So the yeah, I'll let you kind of break this one down. Point being, correlations are interesting, and they might tell us something interesting is occurring, and they're interesting to think about, but they're never telling us if one is causing the other, right? And sometimes we'll have these completely spurious correlations that aren't grounded in reality and are just a random statistical artifact of the fact that there's a lot of things we can quantify and compare to one another. So beware of spurious correlations. And we'll go ahead and stop there. We'll see you next time.